So as John said, my name is Nicole Starrett, and I'm an electrical engineer at Dielectric. I work primarily in TV and FM antenna design. Today I'm going to be talking to you about near-field drone measurements for broadcast antennas. Before we begin, I want to take a minute to make a special acknowledgement to two groups who were instrumental in developing the near-field drone measurement technique I'll be discussing. The first is Cabell Mertz and Associates for their help developing the near-field process from the very beginning, including collecting and analyzing near-field drone data for multiple sites. I also want to thank Eric Wandel at Wavepoint Research for helping to both develop and promote this near-field drone measurement process. Without these two groups, this process would definitely not be where it is today. Here's a quick overview of what I'm going to be discussing. I'll start with field pattern verification and why it's important for broadcasters of all types. Go over the current methods for performing field pattern verification. I'll then define near field versus far field for broadcast antennas, how we can modify current drone methods for the near field, the HFSS software that aids in near field analysis of antennas, a few examples of data analysis in HFSS and comparison to real-world antenna and drone data, and finally, a summary of this near-field drone measurement technique. So why do we do field pattern verification? Well, first and foremost, is your programming reaching its intended audience? Are you hitting those eyeballs that you want to be hitting? Is your antenna operating as expected? Is it installed correctly? And is it in the correct orientation in the field? Also, if you have an older antenna that's not performing as it once did, what issues might that antenna have? Most importantly, field verification is a reimbursable repack item, so if the FCC is paying for it, why not double check everything? So what are our current choices for field pattern verification? First, we have ground-based measurements. These measurements, whether taken from a sophisticated measurement van or from an antenna on a pole with a field strength meter, are an industry standard tool. However, with FCC requirements of a mobile run of at least 100 feet, about 30 feet off the ground, this measurement process can be quite time-consuming. Also, ground-based measurements have built-in errors due to multipath, time-varying signal strength, and ground effects or reflections. We also have aerial measurements taken by helicopter or drone. I'm not going to talk too much about helicopter measurements today, as they tend to take a great deal of planning and are cost prohibitive for many broadcasters. Drone measurements, on the other hand, are much simpler to implement and are becoming more commonly used. I'll get into this a bit more in the next few slides. Drones have increased in popularity across many industries and are an excellent tool for field pattern verification. Drone measurements are quick to perform and cost-effective, and they also eliminate the statistical analysis needed for ground-based measurements. Despite their benefits, drones do come with a few drawbacks, most of which are imposed by the FAA. The FAA has certain restrictions for flying drones for commercial use. These are listed in Title 14, Chapter 1, Subchapter F, Part 107. These regulations include everything from operating from a moving vehicle to operating over people and have a strict definition for line of sight for drone pilots. The regulation I'll be focusing on is Part 107.51, which is operating limitations for small unmanned aircraft. This regulation includes a height restriction of 400 feet above the ground unless you are operating within 400 feet of a structure called the structure shield. Any measurements that need to be taken outside of the shield require a waiver. The waiver process itself can be complicated depending on your measurement needs. All appropriate regulations for Part 107 need to be identified on your paperwork. You need to demonstrate that the flight can be conducted safely by identifying all hazards and laying out a plan to mitigate the risk associated with each hazard. All required documentation, including a flight plan, must be submitted, and once everything is submitted, you can't amend it. Then once everything is turned in, there's a waiting period of up to 90 days for the FAA to process your request. Due to these restrictions, the quickest and easiest way to use drones for field pattern verification is to operate inside the 400-foot shield of an antenna's tower. I'm going to take a few minutes here to define the far field versus the near field of an antenna and discuss how these regions affect field measurements. The far field of an antenna boils down to the distance from an antenna at which the radiation pattern no longer changes with distance. As you can see from the figure and equation on this slide, the far field region will be different for the azimuth and elevation patterns of an antenna. Radiation patterns measured inside this far field limit, or in the near field, are not yet focused and will have different characteristics than a typical far field pattern. Let's picture a typical top-mount UHF pylon antenna, about 14 inches in diameter and approximately 50 feet tall. At 600 megahertz, the azimuth far field will begin about 1.7 feet from this antenna. However, the elevation far field will begin about 3,000 feet from the antenna. So if you were to measure this antenna with a drone inside the 400-foot shield of the tower, you would have no issues measuring the far field azimuth pattern. The elevation pattern measurement, on the other hand, would be well within the near field of the antenna. Now, you may be thinking, okay, the elevation pattern measurement will be different, maybe a little unfocused, but how far off could it really be? Well, take a look at this plot. This shows the calculated elevation pattern of an antenna at varying distances from that antenna. The dotted line is the far field elevation pattern, and the solid lines are elevation patterns at varying distances up to 400 feet from the antenna. You can see that too close to the antenna, indicated by the blue line on the slide, the antenna radiation is completely unfocused compared to the far field measurement. The farther out you move, the more defined the pattern becomes. But even at 400 feet, the elevation pattern can vary significantly from your desired far field pattern. Let's do a quick recap of our field verification options. There are ground-based measurements or helicopter measurements. Each has their own drawbacks. Then we have drone measurements, which can either be taken inside the shield of a tower or outside it if you can obtain a waiver. Plus, we know from the previous slides that any elevation pattern measured will be unfocused until you're in the far field of the antenna. Now, for those of you thinking, even though it will take longer, I should apply for a waiver and get the most accurate measurement I can, right? Well, let me tell you a little bit about multipath and how it can affect drone measurements in the field. Ground reflections and multipath affect the accuracy of elevation patterns measured with a drone from any distance. In general, the larger the distance between the drone and the antenna, the lower the reflection angle, and the higher the measurement error. For practical purposes, we can assume no energy is directed toward the ground in the very near field of high-gain antennas. So the least error-prone position to measure the elevation pattern is within the 400-foot shield of the tower. So how do we modify the current drone measurement method for the near field to get a quick and easy measurement with as few errors as possible, but also be able to compare that measurement to our desired far field pattern? From a drone operator standpoint, it's relatively simple. Just fly your drone within 400 feet of the tower and stay within that shield. This eliminates the need for other more time-consuming and cost-prohibitive measurement techniques. The only glitch here is we need a way to analyze the near-field data and compare it to factory far-field measurements of the antenna. Lucky for us, we have this nifty tool called HFSS, which can be used to calculate near-field data for any antenna. HFSS is a 3D electromagnetic simulation software tool used to evaluate high-frequency electronic products. Every slotted coaxial antenna manufactured by Dielectric for repack was designed using HFSS. This software breaks down each model into a mesh of thousands of tetrahedra, and as shown in the pictures on the slide, then Maxwell's equations are solved at each vertex or node on the mesh. These are exact calculations at each node, not estimates. Within HFSS, a full broadcast antenna can be modeled and as designed and tested in the factory. This requires a full knowledge of all antenna features to construct the most accurate model possible. For example, each layer of a slotted coaxial antenna is unique, which should be reflected in the HFSS model. Coupling structures, dipoles, slot lengths, pattern shapers, etc. all need to have precise dimensions to calculate the antenna's radiation characteristics. Here we have a few example models in HFSS. Top-down views are shown on the left, while isometric views of the antennas are shown on the right. Top-mount antennas are relatively simple. The model consists of only the antenna and the antenna components as seen on the far right on this slide. As seen in the other pictures, sideband antennas can be a little bit more complicated. Everything in the aperture of the antenna must be modeled. So this could include the tower itself, transmission line or waveguide, climbing ladder, support poles, or any other antennas that are at the same elevation level. Once an antenna has been modeled, the far field elevation pattern is calculated and compared to the final factory measurements for that antenna, as shown here. The factory measured far field elevation pattern is shown in blue, and the HFSS far field elevation pattern is shown in red. The beam tilt is consistent between the two patterns, and the null structure is similar. The comparison of these two patterns validates the functionality of the HFSS antenna model. Since HFSS produces a full 3D electromagnetic solution for the antenna, a near-field sphere can be placed around the antenna at a user-selected distance to calculate the near-field radiation characteristics. The near-field elevation pattern for the antenna is then calculated at points on the sphere. It's important to note here that the antenna center of radiation must be precise between the drone measurement and the HFSS model. Otherwise, the elevation pattern can be significantly skewed. This plot shows the beam tilt variance of the near field pattern between the drone and HFSS measurements when the center of radiation is changed. As you can see, even a discrepancy of a few feet can significantly impact the beam tilt of the antenna. Next, I'm going to go through a few examples of drone measurements compared to HFSS near field data. Here's our first example. This data is collected from a side-mounted 10-layer DSC pylon antenna at channel 36. The blue trace is the drone measured elevation pattern, while the orange is the HFSS calculated pattern. As you can see, the beam tilt and null structure correlate between these two measurements. Here we have the azimuth pattern comparison for the same 10-layer antenna that was on the previous slide. The horizontal polarization is shown on the left, while the vertical polarization is shown on the right. In both plots, the HFSS pattern is shown in red, and the drone measured pattern is shown in blue. With a side-mounted antenna, the azimuth pattern is affected by everything in the aperture of the antenna. So the variance between these two patterns is pretty realistic, going from a perfect computer model to an antenna in the real world. Our second example is a side-mounted 20-layer DSC pylon antenna at channel 30, and this one is mounted on a support pole at the top of a tower. As with the previous example, the beam tilt and null structure correlate between the two measurements. These are the azimuth patterns for the 20-layer example. Notice in both the horizontal and the vertical polarizations, the support pole the antenna is mounted to has less of an effect on the azimuth patterns than the tower did in the previous Omni example. Our third and final example is a top-mounted 29-layer pylon antenna at channel 32. Once again, our near-field beam tilt and null structure correlate between the two measurements. You'll notice the beam on this antenna appears a lot more unfocused than the previous two examples. This is due to the length of the antenna. Since the 29-layer antenna is much longer than the other two, the near-field region for this antenna is much larger, making a measurement at 400 feet appear electrically closer to the antenna. Here are the azimuth patterns for the top-mounted example from the previous slide. Unlike the side-mounted examples, these patterns are unobstructed by towers and support poles in the aperture of the antenna. So what does all this data tell us about the functionality of these antennas? We know that the far-field pattern calculated in HFSS matches the factory measurement for the antenna. And we know that the HFSS near-field measurement matches the drone measurement for the antenna. Therefore, it follows that the measured antenna is operating as expected in the far field. To summarize, this near-field drone measurement technique can be used to ensure the azimuth footprint and orientation of a given antenna, as well as confirm the beam tilt and null structure of the elevation pattern. This method provides a quick, easy, and cost-effective way to validate antenna operation in the field. Before I take your questions, I wanted to quickly share a couple of photos I took at a recent drone measurement here in Maine. We're very fortunate here at Dielectric. We have the WGME tower just up the hill, and I was able to walk up and actually see these drone measurements in action, which was incredibly cool. This drone itself is about 4 feet across. So there's not a very good scale in these pictures. but it's owned by LS Telecom. And I had, like I said, I had the opportunity to go up and see this drone in action and meet the team responsible for piloting it. And it was a great experience from someone who deals mostly with the data side of things in my office. Thank you very much for your time, and I'll take everybody's questions now.
Okay, and if you have questions for Nicole, please put those in the Q&A and in the chat. Great presentation, Nicole. Thank you so much for doing that. And so we'll go to Trey for our first question.
Well, I just have a question on my own behalf, which is when the measurements are made, is it sort of like you have a autopilot program, the drone goes in and goes around and makes the measurements, and how many data points are we talking about? Are we talking about thousands or millions, or could you just elaborate on that a little bit?
Definitely thousands. I don't have all of the specifics on the drone data because that is taken by the drone measurement company themselves. But they do have a specified flight plan, and I got the opportunity on site to ask them how they set that up. And I guess what they told me is they have set flight plans for each antenna site that are automated. But in order to get to the flight plan, they have a drone pilot on site that flies the drone up to a certain altitude, and then the automatic program takes over from there.
Very good, Nicole. Barney, a question for Nicole.
Yeah, one of the questions that came up was any experience with HFSS at medium or long wave frequencies?
Yes, so I have personally examined structures in HFSS from low band VHF all the way up through UHF, and then also the FM band as well. So I've looked at most of the frequencies that people broadcast on in the US. So the examples in my presentation were just for UHF, but this process could be applied to VHF or FM as well.
Okay, Nicole. Trey, another question.
Sort of a follow-up question that somebody wrote in about the flight plan that the drone flies.
Sure.
Is it important that the drone fly close to a circle around the tower because you don't want to vary the distance from the radiation point too much?
It is. I don't know the specifics of what tolerance they use to create those automatic flight plans, but they do try to keep as best they can to a set circle around the tower to both keep within the shield of the tower when they don't have a waiver and keep your measurements consistent.
Good. Barney, another question for Nicole.
Is it not necessary to measure phase as a function of at position? And if so, what does one use as a reference phase?
For these measurements, phase is not important. You can get a general idea of the radiation characteristics from amplitude alone.
Okay, Trey, another question.
Are there any limitations in size of equipment on drone versus helicopter measurement equipment and measurements that it might make?
I don't know a lot about helicopter measurements, so I can't comment on that piece of it, but I did have a good conversation with the drone pilots that were here, and they talked a lot about the types of antennas that they mount to their drones and weight versus battery life. They have to be very careful about how much weight they put on the drone because any additional weight reduces the battery life and the flight time of the drone.
Okay, Barney, another question.
There was a question: is who makes the HFSS software?
Oh yes, that's something I should have included. HFSS is an ANSYS product. It's known as HFSS or Electronics Desktop, and it's a wonderful program. I've been using it for about 6 years.
Okay, thank you, Nicole. Trey, another question.
So the remaining question I have on this list says, why was one of the antennas so directional? But I'm not sure I remember which slide that applied to.
Hang on just a second. Let me pull my slides back up. Assuming they're referring to this antenna. So this antenna was just the antenna, or the radiation that the customer wanted was a cardioid pattern. These are just 3 examples I chose out of the drone measurements I've done so far. But we make antennas in every radiation shape you could imagine.
Beautiful, thanks.
Nicole, on slide 21, there's some differences between measured and modeled. Did you talk about that?
Sure. Slide 21. Yes. So my HFSS model that I make for these drone measurements is only as good as the information I'm provided as to what's on the tower. So with side mount antennas in particular, you expect a certain amount of discrepancy between, especially in azimuth patterns, between your real world measurement and your HFSS model, because it's impossible to simulate every nook and cranny on that tower.
Okay, very good. Barney, how about another question?
I partially related to the question about directivity. Isn't there a historic demand for directional FM antenna, for an FM antenna on the edge of a market to try to get penetration, better penetration in a particular market?
I don't, so I'm a relatively new engineer at Dielectric. I've been here for 6 years. I have experience in both TV and FM. However, I don't know a lot about the historic demand for FM antennas, so that's a question I can't answer. I'm sorry.
Okay, Trey, another question.
That's all I have at this time.
Okay.
All right, very good, Nicole. And Barney, any further questions on your side there?
Maybe this is an obvious question, but I'm wondering whether I gather this is only working with dielectric antennas, your work, and the testing you do.
My work so far, yes, has only been with dielectric antennas. However, I'm confident that provided enough information about the antenna, I could model just about anything. So the likelihood of one of our competitors sharing that information with us is slim, but luckily for Repack, we were able to obtain a significant portion of the business, so we have most of the data for the Repack antennas anyway.
Nicole, have you thought about transmitting on the drone instead of receiving?
I can't speak to that myself. I would have to contact the drone measurement company and see what they've played with. I know that LS Telecom, who we've been working with for the last few, are constantly improving the antennas and receivers on the drone itself. So it wouldn't surprise me if they've done something like that.
How long does it take for you know, a drone measurement system to, I mean, is it hours, is it days? How long does it take to gather the data?
The drone flight itself is about 20 minutes. It's really impressive what they're able to do. So they fly up with a horizontal antenna first and measure the azimuth patterns, and then they fly up with a vertical antenna and measure the elevation patterns. It's incredible to watch and very quick.
Wow. Trey, do we have more questions?
Yeah, do you know any specifics about the antennas that are being used on the drone?
I know that the LS Telecom at least is using Yagi antennas, but I don't know the specs on those antennas.
And Barney, do you see any other questions?
I do not.
Okay. Well, Nicole, thanks very much. Oh, here's another one.
Popped up.
Yeah, let's go with that one, Barney.
Does Dielectric do this as a service or just to measure their own antennas?
We provide this as a service. It's typically billed out through the drone company themselves. So a broadcaster can communicate directly with the company that does the drone measurements, and then they communicate with us to get the near field data from HFSS.
And can that be used for verification to the FCC?
I believe so.
So we're on here this afternoon with Nicole. She's from Dielectric, one of the engineers up there, and we're talking about drone measurements of FM and TV antennas. And want to make sure that we do have a survey that we'd like you to fill out about the various talks today. And the information for that was just put into the chat by Amy Beckham. So you can click on that to give the RCA presenter survey. And don't forget, you need to make sure you attend the awards Zoom that immediately follows this Zoom. It is on a different link. So if you haven't registered, you can still go to the Radio Club of America and .org and register for that. We'll be giving away 2 ICOM radios, courtesy of ICOM America and DX Engineering at the end of the banquet. And you have to be on Zoom at that time, so to be eligible for the drawing. And do we have another question, Trey, that came in?
Yeah, one question came in saying, are you familiar with, or could this drone measurement be used, say, for a satellite Earth station type antenna to measure its characteristics?
That's a new one for me. I'm not sure. I would have to contact the drone company and find out what their limitations are.
Okay. Any other questions, Barney?
Oh, there was one about if you've watched these, you know how many loops it makes around the actual tower, the drone while in operation?
The flight that I was able to watch, I was standing at the base of the tower, and for those of you not familiar with the WGME tower, is incredibly tall. It's like 1,200 feet tall, and so I wasn't sure exactly how many loops it made while I was there. I should have asked that question. And
Trey, another question for Nicole.
Yeah, Jim Breakout just chimed in and said, could you tell us a little bit about what types of antennas Dielectric makes and what the main market is?
Dielectric makes a wide variety of antennas, from TV, both UHF and VHF, as well as FM markets. We also have international markets for different frequency bands. So we really have a wide range of products that'll cover just about everything.
Barney, any further questions, Barney?
I am unmuted for a second. There was a question about, can you speak to the drone's location orientation, how it's maintained so tightly in the RF environment?
Sure. So this was something I asked the drone pilots while they were here also. As your drone is flying around the antenna, they will typically ask the broadcaster to reduce power. The amount that they need to reduce power is dependent on how comfortable the drone pilots are with how much power is coming out of your antenna. But if it gets into a high power environment, the drone will cease functioning temporarily. It does have safeguards to stop it from tumbling, and it has automatic positioning to keep it in its path, even with strong winds, not incredibly strong winds, but some strong winds and other weather.
Nicole, what is the highest antenna above ground that you have taken data on?
Gosh, I would have to check the data for the height above average terrain, but I want to say it's the one right in our backyard, WGME. The WGME tower, when it was built in the 40s, was actually the tallest man-made structure in the world for a while. So it's pretty high up there.
Yep. And refresh me, that's about 1,200 feet, is that right?
Yes, about 1,200 feet. I don't remember the exact height.
Okay, very good. Barney, any other questions there?
There is one. Do they use any other FM software like FICO, CST?
I do not personally use that software, no.
Okay. Well, Nicole, thanks very much for coming on today. And we appreciate all this info. It's great stuff. And years ago, we couldn't imagine doing this kind of stuff, being able to prove out the gain of an antenna, the pattern distortion. So that's all very good. And